Now that we've looked at what indefinite integration is, we need to practice doing it. Of course, at this point, what we have are the basic rules based on the fact that we know how to do derivatives. But now we want to introduce a major technique called the technique of substitution. And that's going to be what we're going to look at now. So the substitution method of indefinite integration. And this really is a major technique. Let me give you the idea of this technique. Really what it is running the chain rule backwards. Watch this. Suppose you have the situation where big F prime is equal to little f and G prime exists. Now the only reason I'm mentioning all of this is because I need to talk about the derivative here in just a moment. Now if f prime, large F prime of x equals little f of x, that means large F is an antiderivative of little f. And that will have bearing in a minute. Now the chain rule says the following. Remember this from derivatives. If you take the derivative of the chain of the composition of big F with little g, then what you do is you take the derivative of the outside, so you get f prime, large F prime of g of x, and that is the outside or outer function, which you take the derivative of first, and then you take the derivative of the inside, which in this case is little g prime of x. So there's your inside. Now what we're going to do is really just run this backwards. If this derivative of big F of g of x equals this, then that means if I take the antiderivative of this, I should get this function back, plus a c, of course. So that's all I'm going to do is reverse this and put the antiderivative symbol here. So the antiderivative of big F prime of g of x times g prime of x dx. The dx goes with the integral sign, of course. And here is the function that is the integrand. That is equal to big F g of x, whatever function's in here, plus c. Now, of course, big F prime equals little f, so I could really replace this by little f. And that's what I will do on this next page. And we will get out of this the method of substitution, believe it or not. So, from the previous page, replacing big F prime by little f, I have little f times of g of x times g prime of x dx equals big F of g of x plus c. And now what we do to simplify this, because it looks rather complicated, is to say let's let g of x equal a single letter. The letter will be u in this case. So let's let u be equal to g of x. Then what that means is if I take du dx, that's the same thing as g prime of x. And if I do a little algebra here, I can say, therefore, that du is equal to g prime of x times dx. And what I've got here is what I'm going to later call a translation box. And we'll continue to keep this note up here as we go. Call this a translation box. What I am doing is translating this indefinite integral, this whole equation here, from an integral in x to one in u, and hope that that's going to make things simpler. Now, by this substitution, I now have the integral of f of u. G prime of x dx, this entire expression just becomes du. And over here I have f of u plus c. And this is definitely simpler. And that's the whole point of substitution. We take something here which makes this first integral look difficult, and by substituting a single letter with the appropriate derivative substitution, we end up with an integral that ought to be easier to calculate. This certainly looks simpler than it did. This is the idea. And it's called, as I said, substitution, because that's what you do. Substitution of u for g of x. And when you do that, that makes, when it works, and as always in mathematics, some techniques work sometimes, some techniques don't work all the time. And this is one of them that works very often, but not all the time, makes integration easier. And it is definitely a major technique. So once you've learned the basic antiderivatives, this is the next technique you ought to be looking for when you're trying to do an indefinite integral. Let me give you an example of how this works in a very simple case, and then we'll explore more interesting cases. Suppose I want to do the indefinite integral x squared plus 1 to the 50th power times 2x dx. Now on the surface that looks complicated. It is elementary in the sense that I could multiply this out, and if I did, I'd have a long polynomial, and I know how to take the derivative of polynomials, or rather, in this case, the indefinite integral of polynomials. But who wants to multiply this out 50 times? So it ought to be some way to make this easier, and substitution will come to the rescue in this case. Here is the translation box. I will let u be x squared plus 1, which is the entire inner part of this parenthetical statement. So u is x squared plus 1. That means du is going to be 2x dx. And I'll show you the reasoning, although I will eventually abandon writing this down. The reason that du is 2x dx is because when you go from u to du dx, the derivative with respect to x of this is 2x. And if the dx is brought up here, you have du equals 2x dx. And that's how that works. So this is the translation box. Every time you do a substitution, you ought to create a translation box like this for yourself that will help you keep organized and also make sure that you do everything that's necessary to make a total translation. So here, although I did mention the du dx, which we will abandon eventually, we have the u and the du replacements, so I can come down here. This integral can now be rewritten, and we hope it's simpler. X squared plus 1 is u, so this becomes u to the 50th. And notice that the 2x dx part becomes simply du. Now this is much easier. In fact, we can do this very quickly. We add 1 to the power, divide by the new power, plus c. Now, here's something that you must always do when you're working on an indefinite integral. Remember, an indefinite integral is a function, so it is in a certain variable, in this case, x. When you get an answer from this, you must return to the original variable, which in this case is x. The u variable, or whatever letter you use, is really your choice, and the final answer has to be in the same language as the original problem. So now I replace this. So this is 1/51st. X squared plus 1 is what u is equal to the 51st power plus c. And that is really nice. I have made this apparently difficult integral simple by doing it with substitution. This is the moral here, and now we're going to look at more substitutions. Now let's start out by looking at some straightforward substitutions, and later we'll look at some more interesting ones. A couple of pieces of advice here before we begin. You will be learning other techniques for integration as time goes on. Remember the substitution technique as your first technique of choice, after you check to see if it's an easy integral that might just come out of a table. Always consider this substitution method first. Very often it'll give you exactly what you need, or at least will simplify the problem to where the other integration technique can take hold. Secondly, and this is just experience speaking, if one substitution that you try fails, you try it, it doesn't seem to make anything easier, try another one. Over time, you'll learn to make a good choice initially, but for a while you're not going to. And even with experience, you'll sometimes make a choice that seems right but doesn't lead anywhere. So if one substitution fails, try another one. Fiddle around a bit, and maybe you'll get some success. All right, let's start off. This is straightforward substitution, so these ought to be fairly easy to think about. Suppose we have the square root of 4x minus 1 quantity dx to be integrated. Well, in this case, the square root is really the problem that I don't like to deal with. So what I'm going to do is replace the inside here, 4x minus 1, by the single letter u, and hope that that makes things easier. So my translation box will be to let u be 4x minus 1. And then du will be 4 dx. And once again, I'll show you this step because du dx, the derivative of u with respect to x, is 4. And then you bring the dx up and you get 4 dx. Now this is almost the last time, maybe the last time, that I'll show you this. Okay, this is a translation box. Just keep in mind that you should always have one of those. And then now let's see what happens. The 4x minus 1 is replaced by u, so that becomes the square root of u, which I will write as u to the 1/2. Now what's left here is dx. However, du involves a 4 dx. There's no 4 up here. How do I deal with that? Well, one way to think about it is, I'll just put a 4 in here, and then put a 1/4 out front, because 1/4 times 4 is 1, and that doesn't change anything. The 1/4 out front, however, will carry down, and I'll have 1/4 here, and then the 4 dx is really du as it is indicated here in the box. Some people like to do a substitution in here where they rewrite dx as 1/4 du, a little algebra, so they have it directly in front of them, and then they just make that substitution for dx. I like it this way. Put the 4 in and then the 1/4 to keep in mind that you're doing some compensating. But it doesn't matter how you think about it. The end result is you should have 1/4 the integral of u to the 1/2 du here. And this is now what replaced 4 dx. Well, this integral is easy. This is 1/4 u to the 3/2. You add 1 to the power and divide by the new power plus c. And then once again, return to the original variable. You must always do this whenever you're doing an indefinite integral. So this is now going to be 1/4. This will be 2/3, so I'll have 1/6 times 4x minus 1 to the 3/2 plus c. There is the indefinite integral here completed with the plus c, so it really is an infinite family of functions. It's in the original variable x, which is what I wanted. Remember, too, that when you're going from the x's to the u's, here's something that will play a part later, but I want to go ahead and indicate it now. Always make a total change from x's to u's. That is to say, never mix variables. When you're doing integration, your temptation is to replace easy parts like 4x minus 1 by u and deal with the dx part later, but do it all at once. This integral is all in x. This integral at the next stage is entirely in u. And then it becomes a u function here, which is then changed back to an x function. Do not mix x's and u's in the same line. Okay, well, that integral actually is part of a pattern. As above, the one we just saw, where the function f of x was the square root of 4x minus 1, we can draw a larger conclusion from that. If you have a situation where you have an integrand that has a function of another function, a function of ax plus b, just like this function is of 4x minus 1. If this function is in the integrand, and perhaps I should call this g so we don't confuse the issue here, because the function in this case would really be the square root function. If f of ax plus b is in the integrand somewhere, and whatever this function f is easy to integrate, as the power function 1/2 was here, then the substitution that we made always works. If you let u be equal to ax plus b with du equal to a dx, that works. Because multiplying by a constant or adding or subtracting a constant here will not affect the derivative except by some multiplication of a constant, which is easy to deal with. So this will always work. All right, that's just a note based on that previous problem. Let's move on to something different. Suppose we have this one, x times the cosine of x squared dx. We want again to use substitution here. The question, as always, is what do I substitute for? Well, there's sort of a natural choice that seems to come up here. X squared seems to be the right thing because that would make this cosine of u, which is certainly simpler. Another fact that comes to mind is that if I let u be equal to x squared, and we'll just reason forward a little bit, the derivative would be 2x. The 2 is a constant, that's not a problem. I can always multiply constants as I need them. But having an x is essential. And look, right here I do have an x. So it looks like that seems to be the right way to go. So I'll let u be x squared, then du will be equal to 2x dx. And I'm not going to write that little step to show you where this comes from. But du dx is indeed 2x, and that's what gives you this. And this is, again, our translation box. And now, translating, u equals x squared makes this the integral with cosine of u. And then I have x dx, but I need to have 2x dx. And again, I'll think about it the way I did last time. I'll imagine putting a 2 in here and then compensating for it by putting a 1/2 out front. 1/2 times 2 is 1, so it makes no difference to the indefinite integral. But having the 2 in here allows me to make a nice substitution. And of course, I've got to keep the 1/2 I put in there. So this becomes 1/2 the integral of cosine u du. That's an easy integral. Becomes 1/2 sine of u plus c, because the derivative of sine is cosine. And then I can simplify it finally, because I have to get back to the original variable, remember, which is x. I have 1/2 sine, let's see, u was x squared, so it's sine of x squared plus c. And again, this is in the original variable, as it must be. Okay, this is beginning to give you an idea of how these substitutions, which are fairly straightforward and easy to find, can be done to give you a final result here. Let's try another one. The integral of e to the square root of x power over the square root of x dx. Again, as an example of a straightforward substitution, it looks like, certainly as a first step, letting square root of x equal u would be a wise thing. Let's do that and see where it leads. So u is the square root of x. I know I'm going to have to take the derivative, so I'm going to rewrite this as x to the 1/2. Then du will turn out to be 1/2 x to the minus 1/2 dx. And I'm going to rewrite that in the square root notation because it'll help me see what to do in the integral. This is 1/2 1 over square root of x dx. This, in this case, is my translation box. Has a little bit more algebra in here, but it is good to keep it, as I said, all in one place. Now, let's see what happens here. In this integral, I notice that this will become e to the u because u is square root of x. That's good. That was my intent. And notice I have 1 over square root of x here, and that's almost the right derivative or antiderivative or differential here to give me du. I need a 1/2. So again, I will imagine that I've put a 1/2 in here, compensated by multiplying by 2 outside. Now the inside becomes e to the u. The 1 over square root of x times the 1/2 I added, or multiplied by, times dx becomes du. So now I have a much simpler integral, e to the u du. And this is easy because e to the u is the easiest antiderivative there is. It is just e to the u. So 2e to the u plus c. Finally, I turn that back into the original variable, 2e to the square root of x plus c. Again, this is the original, or this is in the original variable. Must not forget that. So that turned out to be fairly straightforward, as are all the other ones we've been looking at. Now we're going to go ahead and look at some that are a bit less easy to look at. Time for some more interesting substitutions. The first example here we'll look at is the indefinite integral of tangent x dx. And we'll ask ourselves, how are we going to solve this, and how are we going to use substitution in the process? Well, if you look at this as it stands, there's not much to work with. Certainly replacing u by x is not going to do any good. That's just changing the letter. Letting tangent x equals u is fine, but remember, whatever u becomes, we need to have du lying around. Well, du for tangent x equal u would be secant squared x dx. There's no secant squared here. So we need to do something before we can invoke substitution. That will often happen in integrals. You need to do a little massaging of the integrand. What I will do here is I will do a rewriting and hope that this helps. I know that the sine of x over the cosine of x dx is the same thing as tangent x. Now I begin to see something I might do. If I let sine x be u, that's not going to help because the derivative of sine x is cosine, but cosine's on the bottom. It's not up here where it would need to be. On the other hand, if I let u be cosine x, then the derivative of cosine x is sine x, and it is on the top where it needs to be. So maybe I will just rewrite it this way to keep that straight. 1 over cosine x times sine x dx. And I'm hoping that the sine x dx will turn out to be the du I'm looking for. So let's create a translation box. Let's let u be cosine x. Then du will equal minus sine x dx. That's all I need here for my translation box. And then let's see what happens here. Well, in here, The cosine x is u, so this is 1 over u. This is almost the correct du. There's just a minus sign missing. So if I put a minus in here and a minus out here, again, minus times minus would be plus, so, or minus 1 times minus 1 is plus 1 if you like. So that would compensate, and I'd be able to write negative the integral 1 over u, and then the sine x dx with the minus becomes du. And I have this as my simplified, through substitution, integral. Well, this is easy. This is something we looked at before. This is minus the natural log of the absolute value of u plus c. Going back to the original variable, minus natural log of u was cosine x plus c. I now am finished. And again, this is in the original variable. But let me point out something else here. There's another way to write this final answer. If you don't like having a minus sign out front, you can use the properties of logs to get it out of the way and end up with a solution that is the same as this one, but perhaps a little simpler yet. Since it's minus, which is minus 1 multiplied out front, we can think of that as the power of the expression in here. That's what the log rules say. So we have natural log of cosine of x to the minus 1 power. Be very careful there you don't write cosine inverse of x. This is cosine of x to the minus 1 power, which is 1 over cosine x, also known as secant x. So the answer can also be written as the natural log of the absolute value of secant x plus c. And notice there's no negative sign here. So this is an alternate form of the answer, which you might find more agreeable. So be aware that whatever answers you get can be simplified in the same way that the original integral might need to be rewritten in order to be able to do it. Okay, let's look at another example. This will be a series of examples that I hope will be instructive. X squared times the square root of x minus 1 dx. Let's see if we can do this integral. Well, in this one, the natural choice seems to be something very straightforward, something we've looked at before, in fact. Let's let u be equal to x minus 1, and then du will just be dx. However, that takes care of this part here. But what about this x squared? That's going to happen in some integrals. Luckily, we have a relationship here. The very first line we always write is a relationship between u and x, which means if I rewrite it another way, I have x is equal to u plus 1, just solving for x here, which means I now know that I could write x squared as u plus 1 quantity squared. And since I'm in this box, I might as well do the algebra. Write it out as u squared plus 2u plus 1. There is my translation box in this case. And although this would seem to be all I needed, because of the x squared, it behooved me to go ahead and solve for x here and then write out x squared. Now I'm ready to translate this from an x integral to a u integral. In here, the x squared, we've got it written out, will be u squared plus 2u plus 1. Then this is the square root of x minus 1. That's the square root of u, and I'll rewrite that as u to the 1/2. And then the dx and the du become the same thing, so that's du. This is totally in terms of u now, and you notice that when I multiply the u to the 1/2 through, it's just going to be powers, and that's an easy integral. So let's go ahead and write that out. That's going to be u to the 5/2 plus 2u to the 3/2 plus u to the 1/2 du. And then we add 1 to each of the power and divide by the new power. That will give me 2/7 u to the 7/2 plus we have a 2 here, so it'll be 4/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. Finally, again, we return to the original variable. Since u was x minus 1, we substitute, and we are done. This is 2/7 x minus 1 to the 7/2 plus 4/5 x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus c. And there you go. This is the correct evaluation of this initial integral up here. Now, you probably didn't expect that that's what it would be. That's one of the other advantages of substitution. You can make it into a simple integral and then solve it and get a result that was unexpected. All right. Remember the translation box, that it may be more complicated, and remember to put the c in and the other issues that come in to integrate indefinitely. Let us now do a more complex sort of example. Suppose you have cosine cubed dx. And we want to find out what the indefinite integral is here. Well, this one raises all sorts of problems. First of all, we have the same problem here that we had with tangent, which is what will u be equal to? If u is equal to the whole thing, we would need to have a derivative involving the derivative of the whole thing, and that's certainly going to involve cosine. It certainly involves sine, because the derivative of cosine is sine, minus sine. So we have no minus sign up here, so somewhere in there we're going to have to find a way to get a sign if we're going to do this integral. So let me remind you of the advice I just gave. When choosing a u, look for du. If you're going to choose something to be u, look and see if you have the right derivative lying around. If it's not there, you're going to have to work to get it. And we're going to have to work here. So let us see. We need to find some way to get a sign in there. What we'll do is use a Pythagorean trig identity here. This one will be the one that relates sine and cosine. We'll use this to help. So before we do any work underneath the integral sign, let's take this outside and see if we can get to the point where we have something we can integrate. Cosine x quantity cubed, which is what this means, can be broken apart as cosine x times cosine x quantity squared. Cosine x squared is part of one of the trig identities, and we can rewrite this in terms of sine x squared. So this would be cosine x times 1 minus sine squared x, to go back to that other notation. And so I could rewrite this as cosine x minus cosine x times sine squared x. Now, this is more promising. This will actually lead us to the place where we can do the integral. So having done this bit of algebra and trigonometry, we can go back to our integral, which is cosine cubed x dx, replace the cosine cubed by what we just did, which is cosine x minus the cosine of x times sine squared x, all times dx. I will now break this into two integrals and see that I will be able to do both of them. The integral of cosine x dx is 1. Well, that's easy. That's a simple elementary integral. And this one is the integral. I'll put the sine squared up front. Sine squared times cosine x dx. All right. This one, as I say, is straightforward. We can do this in one step. This one, however, will require substitution. So let's just let u be equal to sine of x. This, after all, is what we were trying to get to. Not exactly what we thought we'd get to. We thought that u would be cosine x or some variation on it in the beginning. Turns out it's going to be sine x. If u is sine x, du is cosine x dx, which means I have u squared and I have exactly du here. So this is a wonderful translation box. And notice I'm only using substitution on one of the two integrals. So here's my translation box again, just to keep it marked. Now I can go ahead. This integral can be done directly. Sine x is the antiderivative of cosine x because the derivative of sine x is cosine x. So this is direct. And notice, too, that I'm putting no c yet. Antiderivatives always require a c. I'm putting that off till the end. Minus, and now I make the substitutions here, so this x integral becomes a u integral. This is u squared du. Easy to do. So this is sine x, of course. We carry that along. This is u cubed over 3 plus c. Now is where I put the c. I waited until I got both of them and lumped all the c's together at the end. Then finally, u here was sine x, so I can now write this as sine x minus 1/3 times sine x quantity cubed plus c. And there I have done this integral using substitution in one part, whereas the integral originally looked like it was going to be impenetrable, at least for a little while. So I hope you've got some experience now doing substitution, because now it's going to be... It's your turn now. Some exercises. Here's the first one. The indefinite integral of e to the x all over 1 plus e to the 2x dx. Evaluate that, and then we'll look at what I did. Let's take a look at this. In this case, certainly substitution seems appropriate because this doesn't look like a familiar integrand. I am going to let u be e to the x. Then du, of course, will be e to the x dx, the easiest derivative around. But when I look at this, I see that I have an e to the 2x. And so I probably ought to take into account that. But I know that if u equals e to the x, then u squared is e to the x quantity squared, which is e to the 2x. So now I have everything I need here in my translation box to change this integral over. This now becomes, the bottom becomes 1 plus u squared. The e to the x dx here forms du, so I'll rewrite this with the 1 here and put the du off to the side. I do that so that I can recognize what I've got. Now, you should recognize this is a very familiar antiderivative. This is tangent inverse of u plus c, because the derivative of this is 1 over 1 plus u squared. And then we replace the u by what it is in terms of x. Must always return to the original variable. So it's tangent inverse of e to the x plus c. And we are done. So I hope that's what you got. Let's look at another example, give you a little bit more work to look at. Suppose you have the integral sine x times cosine x dx. Now here's what we want to try. First of all, evaluate this integral with u chosen to be sine x. Then in part B, evaluate this integral with a different u, with u chosen to be cosine x. Now, in part C, the results appear different, as you will see, but of course they must be the same. But of course, must be the same. Because you're doing the same indefinite integral, you cannot get two totally different answers. They have to be the same. Here's what I want you to do in part C. Show that your two answers are in fact equivalent. And we'll talk about this when you come back. Here's the integral we're looking at, the integral of sine x times cosine x dx. In part A, you were asked to say, let u be equal to sine x. Well, let's follow that through. Then du is equal to cosine x dx. So the substitution here is clear. That's your translation box. This will be the integral then of u replacing sine x, and cosine x dx becomes du. That's an easy integral. That's u squared over 2 plus c. And going back to the original variable, that's 1/2 sine squared of x plus c. So there is what ought to be the only answer. Let's try this again with a different u. Our suggestion for B was to let u be cosine x. Then du is going to be minus sine x dx. So I have a negative to deal with. There's no negative up here, so again I will imagine I put one inside and then put another outside so that they multiply out to be 1 and I haven't changed anything, which means that the integral above becomes minus, there's your minus sign, the integral of u du. Well, we've already done this work, so this is minus u squared over 2 plus c. So we will end up with minus 1/2. The u here is cosine squared x plus c. And there is, at least for the moment, apparently a conundrum. There are what look like two different answers to this problem. Well, they have to be equivalent, because this is the same integral after all. There's only one solution. My question for you in part C was, show that these two are equivalent. So let me show you how I went ahead and did that. Here's the answer for part A, and I'll repeat it here. It's 1/2 sine squared x plus c. Now this is where you really understand what indefinite integrals are, that they represent infinite families, and that c is an arbitrary constant. Well, 1/2 sine squared x plus c can be rewritten as 1/2 sine squared x plus c plus any constant I want, because constants can be lumped back in here to c to give me a single arbitrary constant. I'm going to put in minus 1/2 times 1. And this is all because c is arbitrary. And I could lump this back together into 1c if I wanted. Now, what I'm going to then do The reason for me bringing this up, you'll see in a moment. 1/2 sine squared x plus c minus 1/2. And now I'm going to replace 1 by a trig identity, sine squared x plus cosine squared x, which of course is equal to 1. So this part is due to a trig identity. That's that Pythagorean identity we've used before. And now notice what I've got. 1/2 sine x squared minus 1/2 sine x squared, so that adds up to 0. What remains? The c remains, and minus 1/2 times cosine squared x plus c. Well, that's exactly what the answer was for part B. So I have shown that these two answers are in fact equivalent, and I've done it because the c is unusual in your experience with algebra. It represents an arbitrary constant, and whether you add or subtract constants from it, it is still arbitrary. So that means you can play around with it and play around by adding constants, and in this case, rewrite this in what apparently is a different form. So, I hope you enjoyed that.